Greetings. We will in this class conclude the discussion on classical electrodynamics, which is a brief overview of Maxwell's equations and how it connects to the special theory of relativity. What we will be discussing here is examine the trajectories of charged particles in electromagnetic fields, but as seen by two different observers, one who is in this frame, which is a black frame, and the other who is in this blue frame, which is moving at a constant velocity with respect to the black frame. I want to emphasize that this velocity is constant. So both our inertial frames are references, there are no pseudo forces which are involved, but what is electric field and magnetic field for one observer is not the same electromagnetic field for the other observer, and that is the new thing that we are going to learn. The equation of motion, of course, is given over here, that the rate of change of momentum is force. So it is a completely classical Newtonian idea between cause and effect. The force that we are talking about is of course the electromagnetic force, namely the Lorenz force, and this is something that you need over and above Maxwell's equations, other than the boundary conditions of course, that are required to solve problems of charged particle dynamics in electromagnetic fields. The governing idea is that the speed of light does not change from one inertial frame to another, and what changes is time and in fact also space intervals. So these are the governing ideas. Einstein was a very young person when he formulated this in 1905. He must have been about 26 years old, I would think so, something like that. And this connects the special theory of relativity with laws of electrodynamics. So like I mentioned in the previous class, as a result of Lorenz transformations, x, y, z and t, which is time for the observer in the unprimed frame of reference, must transform to x prime, y prime, z prime, t prime, and these transformations are essentially the Lorenz transformations that we are talking about, not Galilean, and therefore t prime is different from t. The trajectory of the particle is given by how the function, the position vector, changes as a function of time, whereas for the observer in the primed frame, the trajectory will be given by how the position vector in the primed frame changes as a function of time in the primed frame, which is t prime, which being different from t. The connection comes from the fact that what is E and B for the first observer is a different mix of E and B to the second observer, which is E prime and B prime, which is not the same. E prime is not equal to E and B prime is not equal to B. That is the essential idea. And therefore, the observer in the second frame of reference can get his trajectory by setting up an equation of motion in the primed frame, which is dp prime by dt prime. Notice that you have the primed symbols appearing over here because the times are different, and then automatically every other parameter also has got a different meaning. Not only that, because E and B transform to E prime and B prime, the force is given by F prime rather than F, because E is no longer E, it is E prime, V is no longer V, it is V prime, B is no longer B, it is B prime, but then in the primed frame you are still talking about the same electromagnetic interaction, namely the Lorenz force. There are no pseudo forces. The solution to this will be given by the position vector in the primed frame as a function of t prime. And now if you solve this equation of motion in the unprimed frame and carry out transformations to the primed frame by Lorenz transformations and then plot r prime as a function of t prime, you will get the trajectory in the primed frame. The other way of getting the trajectory in the primed frame is to set up the equation of motion in the primed frame and express the solution r prime as a function of t prime in the primed frame. Now, these are again completely two different methods. The first method is a Lorenz transformations of the coordinates. The second method involves the relativistic transformations of the electromagnetic field from E b in one frame to E prime b prime in the other, and then setting up a different equation of motion. And if we have done this correctly, then of course the solution obtained using this method must agree with the solution obtained using the other method. The two should generate the same curves in their respective spaces. So, this is the test that r prime as a function of t prime obtained using Lorenz transformations of the coordinates x y z t, or the relativistic transformations of E b to E prime b prime, and solving a new equation of motion generate congruent space curves giving the trajectories. So, here we have the Lorenz transformations, which we have discussed already in unit 6, and these are the transformations of the electromagnetic field. So, what is E x? Is E x prime to the other, but what is E y is not E y prime to the other. E y prime is made up of a mix of E y and B z, and then there is a scaling factor which comes from this gamma. Okay. Likewise, E z prime is not the same as E z, but it is a mix of E z and B y. The mixing coefficient is this velocity, and then on top of it there is a scaling factor which is this gamma. So, E prime is not the same as E, rather it involves superposition of components of E with components of B. Let us look at how the magnetic field transforms. Now, the magnetic field, what is Bx, By, Bz for the observer in the unprimed frame of reference, is a different field given by Bx prime, By prime, Bz prime. These three components give you the magnetic field in the primed frame, and Bx prime is equal to Bx, all right, but By prime is not equal to By. It is a mix of By and Ez, and Bz prime is a mix of Bz and Ey. Now, these transformations equations which tell you how to go to E prime B prime from E and B again are statements of the unity of the electromagnetic phenomenon. You are actually constructing a superposition, adding pieces, one piece is Ey, the other piece is Bz, and you mix Ey with Bz and get Ey prime. Now, when do you mix quantities? Only when they are the same, otherwise you cannot, right. Of course, the coefficients, velocity and everything are such that they take care of the units and dimensions of what you are adding, so that everything will have consistent dimensions. You always add a term to another only when it has got the corresponding dimensions, not otherwise. So, all these things are properly balanced, and that these are some details that I think are good exercises for you to work out for yourself, just to make sure that everything is agreeing appropriately. Over here, mind you that there is a square of the speed of light in the denominator, and that will also take care of the units, dimensions, everything. Okay, so you have to work this out. in full details to convince yourself that the relationships are dimensionally correct. I like to see the unity of electromagnetic phenomenon expressed by these equations very much. In fact, I feel that this is a stronger statement of the unity of electricity and magnetism than Maxwell's equations, because Maxwell's equation express the curl of E, a function of E, in terms of a function of B and vice versa. Over here you actually mix them, and you do know right from your high school days that you mix things only when they belong to the same kind. Okay? So, this is in a certain sense a stronger statement of the unity of the electric and the magnetic phenomena, which was achieved by Maxwell, and then this becomes a precursor to the search for unification of the physical interactions. So, as we know, the nuclear weak interaction is already unified with the electromagnetic interaction. So, that is what is called as the electroweak interaction, and it belongs to the general formalism in physics in which frontier research is being carried out to understand the unification of all the fundamental interactions. So, we will consider some examples now. These are constructs of linear superposition. So, that is the very big feature over here, and many years ago I was discussing this in the Physics 101 course here in IIT Madras, when two students, Satish and Venkatesh, came up, and we had some discussions which led to development of an educational software, which was subsequently published in this issue of Resonance, volume 9, number 7. It was published much after Satish and Venkatesh actually left IIT Madras, because for some reason the software was developed, but we never got the time to write it up, and then the technology became obsolete. The graphic software which they had developed was no longer being used. So, Chaitanya Das and Srinivas Murthy rewrote it later, and then we published it in 2004. So, what I will do is I will demonstrate this particular software. What this does is it solves the problem of charged particle dynamics and electromagnetic fields using two different methods. One in which the solution is obtained in one frame of reference, then you carry out the Lorenz transformations of x, y, z, t to x prime, y prime, z prime, t prime. You get a new position vector r prime, and you plot it as a function of t prime. The second method, which is completely independent of the first method, is it employs the transformation E b to E prime b prime, and I already wrote those transformation relations in the previous slide. Then you set up a new equation of motion with the new E prime and b prime. It is this one. This is the new equation of motion which is set up with a new E prime and b prime, and then it is this equation which is solved to get the trajectory r prime as a function of t prime. So, these are completely two different methods, and then there is a graphics package which projects r prime as a function of t prime, and in fact these projections can be made with the screen identified as the xy plane or with the yz plane or the zx plane. So, you can rotate the coordinate system, so that you, because on a screen you can see the trajectory only on a two-dimensional flat surface, but you can choose that flat surface to be either the xy plane or the yz or the zx. So, all of these features are incorporated in this very nice educational software which was first prepared by Satish and Venkatesh and subsequently by Chaitanya Das and Srinivas Murthy. and this software can in fact be downloaded from my website at this link, so that you can run these programs yourself. But we will show you a few test cases, and what we will do is consider an electron. We have its charge and mass, and we will place it in different electromagnetic fields, and I am going to invite Gagan and Jobin to demonstrate this for you, because they know how to run this software much better than what I do. So Gagan and Jobin, will you please come over and demonstrate this software?
So this is the first case we are going to demonstrate, in which all the components of electric field is actually 0.
Okay.
And we have a Bx which is 0.1 Weber per meter square.
0.1, that is measured in terms of Webers per meter square. Okay.
And the initial velocities are given. Vx is 4.6 into 10 raised to 7. And Vy is 2.65 into 10 raised to 8.
This is the initial velocity of the electron. Of the electron.
Yeah,
okay.
Yeah. And this V relative, that is 2 into 10 raised to 8.
Okay.
This
so this is the velocity of an observer, of a second observer,
yeah,
who is moving with respect to the first observer.
Yes.
At 2 into 10 to the 8, is that meters per second?
Meter per second.
Okay, so that's fairly high speed, because 3 into 10 to the 8 is about the speed of light. So this is at 2/3 the speed of light, roughly,
yes,
right?
Yes.
So this is a fairly high relativistic speed, and which is 2/3 the speed of light. So okay, so let's put it. Let's put this electron in this field. Okay, so this is the software which was developed by Satish, Venkatesh, Chaitanya Das, and Srinivas Murthy. What is this CAPE IITM? That's computer aided physics education, I believe. Computer aided physics education at IIT Madras. So that's the CAPE IITM. That's it. All right. So what are you doing now, Jobin?
This we are just putting the electric field along x-axis,
Okay.
y-axis.
And these are the parameters that you chose.
Yes. Then
So
the
essentially
magnet.
you're specifying the value of the electric field. And okay.
Magnetic field 0.1.
0.0.
All right. And then
And Vx is
Vy
4.6.
and Vz are both 0.
4.6.
4.6 into 10 raised to 7. That is the x component of the velocity.
Oh, this is the initial velocity of the electron.
Electron, yeah.
Okay.
And Vy is 2.65 into 10 raised to 8
2.65.
into 10 raised to 8.
Okay.
65.
Okay. So, all right. So the initial velocity of the electron has got an x component and a y component, and 2.65 into 10 to the 8. And what is Vz?
It is 0.
Vz is 0.
Yeah.
Okay.
And the relative speed.
And it is 2 into 10 raised to 8 meter per second.
And enter your particle parameters. So this is Gagan's electron.
Yeah. This is the charge of the particle.
Yeah.
Minus 1.6 into 10 to the
That's so many
19.
coulombs.
Yeah.
Yeah. And next is the charge mass of the
The mass
electron.
of the electron.
That's 9.1 into 10 to the minus
That's
31
in
kilogram.
Yeah.
Okay. Now go.
Now-
All right.
Continue.
So what is the program doing? It has already finished the calculation.
Yeah.
is it?
Yes.
Okay. And now you get
The
solution.
particle is initially the particle is at the origin.
Okay.
X is equal to 0, y is equal to 0, and z is equal to 0.
Okay.
Now let us run this
This is the trajectory that you see.
as observed from the S frame or the rest frame, you can say.
Okay. Oh, this is the projection on the XY plane.
Yeah.
Yes.
Okay. And this is on the YZ plane.
Yeah.
Yes.
This is the projection of that trajectory on the wall.
So
Now this is on the ZX plane.
ZX plane.
Yes.
Okay. And what is this?
This is the trajectory of the particle what the observer in the primed reference frame see.
Okay, so now the same trajectory as would be seen by another observer who is moving with respect to the first observer
Yeah.
at the velocity that you specified earlier.
Yes.
And that trajectory will be different, and it is shown to be what it is. But there are two panels over here. What is
Yeah.
that?
One is using this field transformation method.
Okay.
and another is using point transformation method.
Okay, so on the left panel, you get the solution not by solving any equation of motion. You have already solved that equation for the first observer,
Yes.
and you just carry out the Lorenz
Transformation.
transformations of x, y, z, t to x prime, y prime, z prime, t prime,
Yes.
and plot r prime as a function of t
Time,
prime.
yeah.
That's given in the panel on the left.
Left.
Whereas what you have on the panel on the right is you set up a new equation of motion, not with E and B, but with E prime
prime
and
and
D
B
prime.
prime.
Integrate f prime equal to dp prime by dt prime, and then plot r prime as a function of t prime, and at least on the yz plane the trajectories are congruent. So thank you, Gagan and Jobin, and then let me
This one is that.
carry on this discussion. So essentially what we did was to compare the observations of two observers, one in the black frame and the other in the blue frame, the blue frame moving at a constant velocity with respect to the black frame, and we obtained the solutions using completely different techniques, one using Lorenz transformations of the x, y, z, t to x prime, y prime, z prime, t prime, the other in which we set up a new equation of motion with the Lorentz force being F prime, which is charge times E prime plus V prime cross B prime, and then integrating that, and we found that the two solutions are quite congruent to each other. These are some of the cases that we considered to illustrate this, and thanks to Satish, Venkatesh, Chaitanya Das and Srinivas Murthy, and also to Gagan and Jobin for showing this nice software to us. And I will conclude by giving a very brief summary of writing the equations of electrodynamics and tensor notation. It is not something on which I will spend any bit of time, but it is something that you should be familiar with, because once you have seen this you will then be able to read literature on this subject from any source. So you need a little bit of familiarity with the notation. There is no new physics in it, there is only a new notation. So let me just introduce you very briefly to the notation. We do know that the electromagnetic field is expressible in terms of potentials, you can derive it from potentials, and in tensor notation what we do is write contravariant vectors in this form. So x mu takes these 4 values x0, x1, x2 and x3. So mu takes 4 values 0, 1, 2, 3, and the covariant notation appears as a subscript over here, the contravariant notation appears as a superscript over here. So this is the relationship between the contravariant and the covariant notation. The signature that I make use of is this 1 minus 1 minus 1 minus 1. This is what distinguishes the space time continuum from an ordinary extension of the Euclidean space to 4 dimensions. So it is not an ordinary extension of the Euclidean 3-dimensional space to 4 dimensions. This is the space time continuum coming out of the special theory of relativity, and this is the signature of this metric G. And you can go from the covariant notation to the contravariant notation in a simple fashion by using this matrix notation. You can just use this as matrix like matrix algebra, and these are the relations which you use to get the electromagnetic field from the potentials. So as you can see, here you have the derivatives of A mu, and these derivatives, the A mu itself is a 4 vector. The 3 components of what we call as a magnetic vector potential, and this is the electric scalar potential. Together they give you 4 components which are A mu, which are of course A0, A1, A2 and A3, and these are derivable. You know, when you take the derivatives of this electromagnetic potential, you get the corresponding electromagnetic field. So, the electromagnetic field is now written over here. The right hand side gives you the derivatives of the potentials and the left hand side gives you the components of the electromagnetic field. The notation is sometimes made a little more abridged. You can write this del by del x mu as del mu and this one as del mu. Notice that there are covariant and contravariant indices to keep track of. So, now these are the Lorenz transformations that we had. I have used a barred frame rather than a primed frame, but it is the same thing. Okay. I just needed a different notation to express the fact that you have one frame of reference which is moving with respect to another, and this is the transformation of the which gives the Lorenz transformation, and you can go from the parameters in one frame to the other by carrying out these transformations, and you can write them in a very compact manner by this transformation matrix lambda. This is the uppercase lambda and this is the transformation matrix, and you can go from one frame, the normal frame without the bar, to the corresponding parameters in the other frame which has got a bar, or the primed frame if you like. So, on the left hand side I could have used a primed a mu prime instead of a bar mu. Okay, it is the same thing, and the electromagnetic field in fact is very conveniently expressed as an antisymmetric tensor which has got a very simple form. Notice that there is some sort of a symmetry about the diagonal, but this is more like anti-symmetry because the terms over here have got opposite signs. So, if you go equidistant away from the diagonal, then the corresponding terms have got opposite signs. So, this is T23 and this will be minus T23. Okay. So, T32 is equal to minus of T23. So, when you interchange the indices over here, you pick up a minus sign. That is what makes this tensor to be antisymmetric. So, in this notation you can write the electromagnetic field. The electromagnetic field in our usual vector notation is made up of Ex, Ey and Ez. So, they are appearing over here. This is Ex, this is Ey and this is Ez, and in terms of this antisymmetric tensor, the electromagnetic field is expressed by this 4 by 4 matrix which is an antisymmetric tensor. Again you have zeros along the diagonal, okay, just like this typical antisymmetric tensor. Again you have an antisymmetry over here. So, if F01 is Ex over C, then when you interchange 0 and 1, so instead of the element in the second column and first row, you go to the element in the second row and the first column, you get minus of F01. So, this will be minus Ex over C, and likewise you will have other components to be given by the corresponding antisymmetry. So, this is just a matter of notation. Essentially what you have written is the electromagnetic field, there is nothing new in it. Here this is the electromagnetic field over here. So, you have the x component over here, you have got the y component over here, you have got the z component over here, then you have got the magnetic field over here. So, the Bz is here, the By is here and the Bx is here, right. So, this is just the electromagnetic field, there is nothing new in it, and the compact transformation relation can be written for a first rank tensor which is a 4 vector now instead of a 3 vector. Now, this is the transformation rule for the first rank tensor. The electromagnetic field is the second rank. Yes, yes, okay, all right. The corresponding transformation rule for the second rank tensor is given by this, because there are two indices to play with in this case. So, this is the transformation rule for the second rank tensor. This lambda we have already defined, and Maxwell's equation, the same Maxwell's equations that you have seen earlier, are written in a very compact manner and in this particular form. So, this is a set of equations, these are the Maxwell's equations. J mu is the density, this is the current density 4 vector. So, it has got the charge density as well as the current density, which we have met already in the vector notation in which Maxwell's equations we developed earlier. And let us just satisfy ourselves that this notation gives us consistent relationships which we have seen earlier in the ordinary vector notation. So, you have the Maxwell's equations and you have got the current density 4 vector, and if you just take the particular case, put mu equal to 0, then all I have done over here is to put mu equal to 0. So, this is del by del x nu of f 0 nu, and this index nu which appears twice is the one over which you carry out the summation. This is sometimes called as the Einstein summation convention, and you must sum over this index nu going from 0 to 3. So, let us do that. So, the term corresponding to nu equal to 0 is here, this is nu equal to 1 term, this is nu equal to 2 term, and this is nu equal to 3 term, and Maxwell's equations take this form. Now, let us see if it is the same as we have seen earlier, because we do know that these are the electromagnetic field terms. So, F00 we have already seen is 0, this is coming from the anti-symmetric tensor for the electromagnetic field. F01 is Ex over c, F02 you have to take its derivative with respect to x2, and then F03 is Ez over c, and you have to take its derivative with respect to x3, and you already know what these terms are. So, just take those derivatives term by term, and what you get means the first term of course will give you 0 because F00 is 0. Okay. So, from the remaining 3 terms you get del Ex by del x, del Ey by del y, del Ez by del z, you have got a 1 over c here, you get mu 0 c times rho on the right hand side, but this c you could move to the right side. So, you will get mu 0 c square, and that is 1 over epsilon 0. Okay. So, what you get essentially is that the divergence of E is rho by epsilon 0. In other words, this equation gives you the complete family of Maxwell's equations, and you can put in the other values of mu and do this as an exercise for yourself, and satisfy yourself that all of Maxwell's equations can be written in a very compact form in this tensor notation, which you will find being used in a lot of literature on classical electrodynamics. So, it is good to be familiar with that. So, with that I would like to give you a set of references which you could use to read these topics further. Berkeley physics course is one of my favorite sources. The volume 1 which is by Kittel, Knight and Riederman, and Purcell's volume 2 which belongs to the same series, the Berkeley physics course. So, these two are excellent sources. Feynman lectures are of course great. Griffith's book also gives you all the essential tools, and then there is a nice book by Matveev, Mechanics and the Theory of Relativity, and this is a nice source to read about current problems of current interest, modern problems in classical electrodynamics. And then the reference to the software which I mentioned, the KPyTM, the computer aided physics education program that we have. It's not a huge program, but there are a few attempts made by some students who have the enthusiasm to develop some educational software. They contribute to this, and with that we pretty much conclude this unit. If there are any questions, comments, I will be happy to take. Otherwise, we will go over to the unit 11 in the next class, which will be on chaotic dynamical systems.